Okay, the first thing we're going to talk about is section 7.1. And here's the cool thing about 7.1 is we're going to talk about exponential functions. And I'm just going to show you something really quick on the calculator. Okay, I don't know if you guys are basketball fans, but you know, right now is March Madness. And I forgot the guy's name that offered $1 billion. Okay, if someone could fill out a perfect bracket for the NCAA tournament, $1 billion. Okay, well, why in the world would someone offer someone $1 billion if they could fill out a perfect bracket? Okay, so he said you're more likely to win the lottery because do you think that does he think that anyone's going to fill out a perfect bracket? Okay, well, so let me tell you how it works. Okay, that first round, first of all, we're going to say 64 teams. They've kind of changed the rule and there's really 68, but originally there's 64 teams in the NCAA tournament. Okay, so if I wanted to figure out how many different ways someone could fill out that bracket, it's an exponential function. Okay, it's actually 2 raised to the 64 power. All right, because there's 64 teams, okay, and they're going to play against each other. So look at what the possibilities are. Okay, first of all, that number is so big, it's in scientific notation. And that 19, e to the 19 says take that decimal point and move it to the right 19 times. Okay, that's how many possible ways that you can fill out that bracket. So just in case you're curious, the first round, okay, there's those 64 teams played each other. There was one round, and there was one person. Yeah, one person that still had a perfect bracket, but he didn't enter the contest. Okay, I don't know, he just didn't. But then after the next round, no one had a perfect bracket anymore, and that was just after the first round. Okay, so it's just kind of in the example that I have for today's lesson, you received those emails that said, have you ever received an email that tells you to forward it to 5 friends? And then each of those 5 friends are supposed to forward it to their 5 friends, things like that. Well, that's an example of an exponential equation. Y equals 5 to the x can be used to represent the situation where x is the number of rounds that the email has been forwarded. So those people grow exponentially. Okay, so the first thing I want you to do, we're just going to talk about what the graph looks like. Okay, y equals b to the x is called an exponential function. And when I graph it, the reason it's called an exponential function is because it grows really, really fast. All right, so it's going to cross at the point 0, 1, and you have what we call the graph of an exponential function has an asymptote, which is a line that the graph of the function approaches. So this is the graph of y equals some number to the x power. B is just a number. Okay. We also have translations of our exponential functions, and I'm going to show what that looks like here in just a minute. And we have what's called a growth factor. So on your paper, you need to either circle or highlight or do something because this is the equation we're going to use. All right. You can model exponential growth with a constant % increase over specific times, but you're going to have to look at this and know what each variable means. Okay. So first of all, examples of exponential growth, bacteria growth. Okay. So those of you that are in biomed, an example would be bacteria growth, population growth. All right. We have growth and exponential decay too. So in this problem, A, all right, is your initial amount that you start off with. Okay. So what is my time, Renee? What is my time when it's my initial growth? What would time be if it says my initial growth is this? It doesn't really say up here. So if I said our initial population in this room is 16 students, what would my time be? When time equals 0, that's my initial growth. So anytime you see the words initial growth, you automatically know that time is 0. Okay? R in this problem is the % of increase per time period. All right, and so we're going to be using that to model population growth here in just a little bit. And then we also have our exponential decay. Here's an example of what an exponential decay function looks like. Instead of going up, it's going to go down. Okay, an example of, well, I don't know if this is a true example, but you might think of when you buy a new car, what happens as soon as you drive that car off that lot? It goes down. The value of that car goes down as soon as you buy it and as soon as you drive it off that lot. If you wanted to sell that car 2 weeks later, you're not going to get near what you paid for it just because now it's not a new car, it's a used car, which that really kind of stinks for you, huh? It doesn't even matter. For example, my car that I bought, okay? My car, when I bought it, was 2 months old. Well, 2 months old? I don't know if it was 2 months old. It had 2,000 miles on it, okay? And so it was like a brand new car, but it had 2,000 miles on it. I think the person that bought it, she either changed her mind or she couldn't make the payments. I don't know. So I got a really good deal on my car because even though it was basically a brand new car, it had 2,000 miles on it, and the price of that car depreciated because it was now considered a used car. Okay. So this is an example of an exponential decay function, and you can see that the graph goes down. And then same equation that we're going to use for exponential decay. A is my initial amount, R is the rate that they're going to give us, and T will be our time. And we're going to use that here in a little bit. And then compound interest. Okay, we're not going to have any compound interest problems today, but we will. An example of when you want compound interest is when you're saving money. When you have a savings account, you want the interest to build up. All right, so here's what I want to do. We're just going to practice graphing these, and then we have to state the domain and range of each. So everyone get your calculators out, and we're going to just do a few of these together, then you'll be able to go back and do the rest. Okay, so let's just start off doing number 1. So enter y equals, okay, and I need to turn my plot off. Okay, you're not going to put anything in for x, because that's part of the equation. All right, so in my y1, here's how you're going to enter this in. I'm going to type in 1.5, and then I'm going to enter it in exactly like it looks on my paper. My 2, close the parenthesis, and then I need my x as my exponent, so I'm going to hit my housetop button, x. Now, let's graph this. Look at the window for number 1. Okay, I don't want to graph it -10 to 10 because I want it to match up the window that they have. What should I set my window to on number 1 to get approximately what they have? Okay, on my x values, looks like they went from -4 to 4. And then on my y values, I'm going to go from -1 up to 9. So you see how I'm making my window match their window? And then I'm going to hit graph. Okay, so we're going to sketch that on our paper. When we sketch it, we need to know some exact points. All right, so I'm going to hit my trace button. When I hit trace, mine automatically put a point down at the bottom for me. It's the point 0, 1.5. So we can go ahead and plot that point, 0, and then up 1.5. And just by looking, I don't know, I'm going to type in the number 1 and see what I get. 3. I get the point 1, 3. And if you'll notice, see how this graph, it gets closer and closer to the x-axis? Okay, it's not going to go below that x-axis. It's going to get closer and closer and closer. Okay, so when you draw yours in, you can get closer and closer to the x-axis. And as long as you have at least those 2 points, you know, I might be able to find another point to the point 26. Okay? So sketch that in, and then we need to also state the domain and the range. When x is 2, y is 6. All right, so on my paper, let's list the domain. So when I'm looking at the graph, how far left and how far right does this graph go? Did you fix it? Okay. All right. From the left, it goes all the way to negative infinity. And to the right, see how it looks like it levels off? But if I keep going and going, it's going to keep going to the right. Okay? So my domain for number 1 would be what? Negative infinity to infinity, or I could put all reals. My range is how far down and how far up does this go? My y values. Well, how far down does this graph go? It gets close to 0, right? But remember I said it never crosses that x-axis? So it gets close to 0, and then it goes up to infinity. So when I write it, I'm going to say 0, and I have to use a parenthesis because it doesn't include 0, to infinity. Okay? Let's do another one. Let's do number 3. So I want everyone to graph number 3. So y equals, and we're going to enter it in exactly like it looks. 3 and then parenthesis 0.5, close my parenthesis, my hashtag button, X. They're using the same window. Okay, this time instead of going up, they're going down. So this would be an example of an exponential decay problem. So I'm going to hit trace, and I have the point 0, 3. So that's one point I can put, 0, 3. If I type in 1, I have the point 1 and then 1.5. I hit trace and I just typed in 1 and then enter. And if I wanted one more, I could type in -1 so I could get one on the other side, and I get 6. So do you see how it's almost the same points as the other one? It's just flipped downward. Okay, so after you sketch it, let's write our domain and range. What's my domain for this one? All reals. So I can either put all reals or I can put negative infinity to infinity. On these, the domain will be all reals for all of them. My range, how far up and how far down does this go? Again, it's 0 to infinity, right? So it's going to look just like the other one, 0 to infinity. Like when you draw the arrow, you would draw it like right there and right here. Yeah. Yes, both places. All right, let's go to, oops. Let's do number 4. Okay, everyone put number 4 in your y equals. Number 4 is 5. My parentheses, 1/2. And that's raised to the x. Now you have to be careful when you raise this to the x, I have to hit my right arrow key so that I'm no longer up there as an exponent, and then I'm going to put my -8. So this -8 is going to translate this graph 8 units down to where it normally is. Now, I also need to change my window. What's my window going to change to? Okay, good. -5 to 5 on my x and my y axis. We're on number 4. Okay, then we want at least 2 points. So I'm going to hit trace. I have the point 0, -3. I can type in the number 1. I have 1, -5.5. Or I could type in -1. So as long as you have 2 or 3 points, now, when we list our domain and range, I already said our domain for all of these will be all reals, but our range on this is going to change. Now, here's the deal. When I look at this graph, because I'm only looking at part of it, it looks like my range goes from -infinity to +infinity, right? Because it looks like it goes all the way up and all the way down. But here's the deal. If I changed my window, we would see that this actually levels off. Just like our others leveled off at 0, this one is also going to level off. So how am I going to know where it levels off if I don't see the entire graph? Well, anytime you have a -8 or a -5, or if I had like a +2 at the end, that's where it's shifting this up or down. So whatever number is being added to or subtracted from, that's going to affect my range. So let's list our domain. Our domain we know is -infinity to infinity, -5 to 5 on my x and y. But my range, instead of starting at 0, it's going to start at whatever number is being added to or subtracted from. So instead of starting at 0, I'll start at -8. So my lowest point on this graph would be -8. And it's going to go up to infinity. It's not included. No. Okay, so without even graphing, let's list the domain for 5 and 6. What would my domain be for number 5? All reals or -infinity to infinity. My range for number 5 would be what? Do I have a number that's being added or subtracted from at the very end? No. This -3 right here, that doesn't count. So it's going to be, where's my starting point for my range? 0 to infinity. Okay, and when you graph that, you'll be able to see it. What's my domain for number 6? -infinity to infinity. What would my range be for number 6? -5 to infinity. And again, when you graph that, you should be able to verify that using your graph. Okay, so is everyone good with numbers 1 through 6? All right, let's look at number 7. Number 7 says the initial number of bacteria in a culture is 12,000. The culture doubles each day. Write an exponential function to model the population Y of bacteria after X days. All right, so here's the deal. I know I'm going to use Y equals, and how do they want to write it? Okay, here's my initial equation. Gabby, put it up. Okay, A is always what? A is always my initial amount. What is my initial amount for number 7? The initial number of bacteria is 12,000. So that's going to go in the place of my A. So I have Y equals 12,000. Now, 1 plus R is always going to be my rate that it's changing. Okay? Well, they actually gave me what it's doing. What is the rate that it's changing? What did they say? It's doubling. So that whole number right here, that whole inside is going to be a 2. They just gave that to me. and then that's going to be raised to the time. But what did they tell me to use for my time? X. So that's my exponential function to model that bacteria growth. Right here? Right here? T, that stands for time. And they told me to use X for my days. Okay? So now how many bacteria are there after 6 days? So I'm going to use this equation, y equals 12,000 2 to the x, but what am I plugging in for x? 6. And then that becomes a calculator problem. Okay, I want everyone to put that in your calculator, see what you get. The 2 is the rate at which this is changing, and it says that it doubles, so that's why I'm going to put 2. Okay, you're going to use the 1 plus r when they give you like a percentage. The R is going to stand for a percentage that they give you, which is we're going to use in the next problem. But if they just tell you what that rate is, it's doubling or it's tripling, then that's going to go in the place of this whole thing right here. Okay? Yeah, what'd you guys get? That is correct. So how many bacteria are there after 6 days? Well, that really goes fast. So they started off with 12,000, okay, and after 6 days, there's 768,000. All right, so look at number 8. Okay, a college with a graduating class of 4,000 students in the year 2008 predicts that its graduating class will grow 5% per year. Write an exponential function to model the number of students y in the graduating class t years after. Okay, so again, here's the equation that I'm using. 1 plus r raised to the t. Remember, a is always our initial amount. What is our initial amount? What did they start off with? 4,000. They started off with 4,000 students. So 4,000 will go in the place of my A. And then this 1 plus R, it says they're going to grow 5% per year. So I'm going to plug this 5% in place of what? R. So I have 1 plus 5%, but I'm going to write 5% as a decimal. So then I have y equals 4,000, 1.05 to the t. And that's my answer. That's the exponential function to model their growth. No, they just want the model. They just want the equation. Okay, so right now, really quickly,